Estoy por acá, estoy solamente tratando de que el fondo no se vea el placar.
Really?
Yeah, yes, it's different.
Yes.
Of what I'm used to. Yes, right?
Yes,
Maria?
like
Yes.
a couple of weeks ago.
Oh, okay. So we wait a few more minutes and then we begin.
Okay. I see that it's stopped the presentation. The thing is that when you do a presentation with two screens, I cannot share a window because the window only opens when I start the presentation. So I need to share the screen. Then when I share the screen, I cannot see any of the...
Yes, that's correct.
Yeah. So, yeah, well.
Hello, everyone. Thank you for connecting. As usual, we wait a couple of more minutes and then we begin. Hi, Manuel. How everything is going well? Yes.
Yes, everything is going okay. What about you?
It's okay.
Okay.
We got our first shot
Okay.
yesterday, both of us.
We got our first shot
Yesterday for the COVID vaccine with Manuel. For the COVID vaccine with Manuel. For the COVID vaccine with Manuel.
Yeah, we saw each other at the hospital post. At the vaccination post. At the vaccination post.
All the vaccinations are given in the hospital?
It was not a hospital.
No, it was not the hospital.
It was a vaccination post.
I see.
It was a vaccination post.
I see.
Are you magnetized now? Are you magnetized now?
So
we can do the trick. It's not working for me. It's not working.
So what type of vaccinations are you getting?
AstraZeneca.
Okay.
AstraZeneca. Yes.
Okay.
That was for me.
Okay.
That was for me.
Okay.
Okay, shall we begin? Well, shall we begin? Thanks everyone for connecting to our seminar. Today we have the pleasure of having Dr. Omer Bromberg, who is an assistant professor at the Faculty of Exact Science of Tel Aviv University. Dr. Bromberg works on various topics related to relativistic astrophysical system and on magneto-hydrodynamic simulation of astrophysical jets. His research includes running large 3D magneto-hydrodynamic simulations of jet formation and propagation, and he studies their physical properties. In particular, today he is going to talk about the energy dissipation in relativistic jets. We thanks a lot, Dr. Omer, Dr. Bromberg, for accepting our invitation, and thanks everyone for connecting. I will ask to mute your microphone, and if you have any question during the talk, you can put it on the chat. So I will interrupt Dr. Bromberg and ask him the question. Also, we have a channel on YouTube that is transmitting live this talk, and we have a question section there. So if anyone is connecting there, they can have
Thank you all for having me and for joining. Thank you all for having me and for joining. I hope that next time I will give the talk. I having me and I hope that next time I will give the talk. I having me. Several of my later researchers, and the one thing that they have in common is that they are all connected with the relativistic jets, and specifically the questions that I'm interested in, what is the physics that stands behind the launching of these jets, and more physics that stands, and more importantly, the energy dissipation. Somehow change back into the presentation. I have no idea how. Okay, this will work. Okay, so since we are in radio astronomy, since we are virtually radio astronomy, it's suitable to start virtually radio galaxies. It's suitable to start virtually radio. So radio galaxies are considered parts of the AGN family, but they also belong to a larger group of physical objects. They also belong to a larger group that contain GRBs, microflash quasars, and also some kind of supernova. So the jets in these objects are different in their scales, as you can see here, stellar scales to megaparsec scales, and also in their temporal and spectral behavior. They are all thought to be powered by roughly the same mechanism. They are thought to be powered by some sort of an electromagnetic mechanism that I will talk about that extract rotational energy from a compact object, usually an accreting black hole, but not only. And the reason for the change in the observational features that we see is in the mass of the black hole, the properties of the environment, the accreted mass, or the observational angle. So if you want to talk about how we launch a pointing flux-dominated jet, I'm going to use this acronym for the relativistic jets because the jets in my talk are all powered electromagnetically. We can think of this following simple model. Assume that we have a perfectly rotating sphere, and it is and we have a magnetic field, a radial magnetic field attached to this sphere. And the sphere is rotating with some velocity omega. Now, due to the fact that it is a perfect conductor and all electromagnetic forces on its surface must be zero, the rotation implied that we have an electric field in the theta direction, which is just the cross product of V cross B on the surface of the conductor. In addition, since there is a condition for a flux freezing, also because it is a perfect conductor, the rotation actually drags the magnetic field. The magnetic field is attached to the surface and is dragged with it. Now, if the surface is rotating in velocities close to the speed of light, what is happening is that basically this creates a toroidal component where it's with a power which is with a value which is roughly equal to the value of the electric field. Now, the cross product of d phi times E theta gives a pointing flux which is directed along the radial direction, and this is basically the energy that is extracted from this body. If we take typical masses of supermassive black holes and magnetic fields in these regions, we can get powers up to 10 to the 48 ergs per second. Now, the only difference between black hole and this simple example that I showed is that within black hole, we cannot have, the black hole itself cannot carry magnetic field, and the magnetic field needs to be continuously supplied by a disk, and I will get to that later in the talk. Okay, so the energy that is extracted from this object is this pointing flux is a very clean energy. It's a very long wavelength, and it is not supposed to be seen. It is not supposed to radiate at all. Nevertheless, when we look at relativistic jets, we see emission coming from vastly different scales on the jet, starting from scales smaller than a few times of the gravitational radius of the jet, up to 10 to the 7, up to tens of millions and hundreds of millions gravitational radii away from the black hole. And also, the observed properties of this radiation are vastly different, both in temporal and in spectral shapes, at the different in the different sites, which imply that first of all there is some dissipation mechanism that is working to transform this electromagnetic pointing flux into the emission that we see, and it is most likely that we see that we are witnessing the result of more than one dissipation mechanism. And the underlying question that I'm going to refer in this talk and in a lot of projects of my work is how does the electromagnetic energy dissipate and transform into radiation? In other words, how this clean energy transforms into something that we can actually see. And what are the particles and acceleration and emission mechanisms that come to play? So in this talk, what I will do is that I will present several activation and dissipation channels in pointing flux dominated jets, and I will discuss the pros and cons in each mechanism, and I will also discuss some observational predictions for this. So let's start. The first mechanism that I want to talk about is known as Kink instability. So what is Kink instability? Basically, whenever we have a magnetic field configuration, which is dominated by toroidal field, this configuration can become unstable, kink unstable. Kink instability basically generates helical twist in the jet, as you can see here in the left image, okay? And this twist leads to reconnection and to dissipation of the magnetic energy, as you can see in the right figure. The basic time unit for the linear growth of the dissipation, since it's a dissipation, it's growth exponentially. It has a linear phase and non-linear phase. So the base time unit for the growth of the dissipation is the time it takes a fluid element to circle around the jet, okay, in the rest frame of the system. If the fluid is moving relativistically, we need to go to the rest frame of the fluid, of the bulk motion of the fluid, and then it's roughly the time it takes a fluid element to circle around the jet. Now, as you can see, that this time is shorter for larger toroidal fields. So when the system is dominated, BP is the poloidal part. In this case, it's the Z direction. B phi is the toroidal part. Is the component, is the ring component, if you want. And in systems where B phi dominates over B phi and RJ is relatively narrow, we get that the system will tend to become kink unstable faster. So in other words, narrow jets dominated by B phi will become kink unstable, and the typical time that it takes this instability to become nonlinear. Nonlinear, it means that you actually see, this is the nonlinear phase, this is the end of the linear phase, if you want. The typical time is about 10 times of this T kink. So this is very nice, but turning the jet into narrow column is something that it is not easy. It's not easy to make narrow jets. So let me give you a little bit of a short overview of jet acceleration and how can we make jet narrow. So suppose that we go back to the initial story that we had. We had this rotational sphere. It had magnetic field attached to it. It's rotated. Now I'm extracting this pointing flux. The pointing flux initially flies along radial trajectory. Now, as this electromagnetic and the plasma particles that are attached to it are accelerating, the acceleration basically, let's see if I think I brought some aid here. So how does a spring accelerate? Do you see this? Everybody see this?
Yes, we can see it.
Okay, so suppose that this is the jet, this is column, but let's assume that it's expand radially. So basically the acceleration of a helical field, the field is basically helical because I had this radial component, I'm winding it, and this winding is expanding outward like a helical wave. So the way that these things accelerate is basically by unwinding. I have like a spring, and the spring is unwinding. Toroidal component is turning into poloidal component. Okay, the spring become more and more unwinding. This is basically the acceleration of magnetized jets. Now, as this thing continue to expand, since the poloidal component, the radial component, is falling faster, this is falls like 1 over r squared, while the toroidal component falls like 1 over r. So if these things would expand and not accelerate, then I'm very fast will become dominated by the toroidal field just because it drops slower. But since I have this acceleration, I'm continuously transforming energy from the toroidal to the poloidal component. During this conical acceleration, b phi and bp continue to be all the time to be comparable to each other. Okay, and in this situation, what's happening is that the Hooke stress, the toroidal component, is acting like a rubber band. Magnetic field has a tension in it, so if you want to expand it, it will object to that and will try to contract back like a rubber band. So this contraction is known as Hooke stress. So the Hooke stress that is trying to take the jet and make it narrow is always balanced by the pressure, by the gradient, the radial gradient of the magnetic pressure, and we're getting force balance, and the jet just cannot self-collimate. It continues to accelerate along radial trajectories. Now, when does the acceleration stop? The acceleration stops when the Lorentz factor is reaching this limit. This limit, what's happening is that the velocity over which the jet expands is just too fast for information to travel across the jet. Fast magnetosonic wave from this part of the jet which try to reach the axis will reach the axis, but they will never be able to bounce back because by the time this thing goes on, the jet already expanded. In this situation, different particles on the jet stop to communicate with each other. And if they cannot communicate with each other, this spring can no longer does not know that it is winded, and it cannot get unwinded. So acceleration stops at this limit. The jet remains highly magnetized, and it continues to expand on conical trajectory because also the Hooke stress is no longer effective because the points are no longer connected with each other. Okay, so relativistic jet cannot self-collimate. So if you want to collimate the jet, I need some outside medium to compress the jets on the side and collimate it. So the two ways that we can think of to collimate jet is by two different types of medium. One medium is a wind medium, as the second one is a stationary. So a wind, you may imagine you have a black hole rotating, you have a disk, and the disk is blowing out wind from the stresses on it and from the temperature, and wind comes up and it interacts with the jet and it collimates. Now, wind collimated jets tend to be conical or parabolic. Okay, like you see here in this image, and they tend to be fast because they are quite efficiently accelerated. Okay, and this configuration is Kink stable because first of all, the jet is becoming wider and wider, and secondly, the fluid there moves quite fast. So this configuration is stable to Kink. The second configuration, in the case of a stationary medium, the jet will tend to be conical, cylindrical, sorry, as you can see here. Okay, and the pressure in the cocoon that this jet grows as they propagate inside the jet tends to be uniform pressure. This jet, the velocity in jet is relatively slow. It's much slower than the velocity in the wind case, and these types of collimation jets will tend to be Kink unstable. So let us talk about jets that are collimated by stationary medium. Okay, in AGN, by the way, both types of this media can coexist. At small distances from the black hole, we see disk wind, medium dominated by the disk wind. The jet tends to be conical, and the velocity tends to be quite fast. At some point, the medium is transforming from a wind dominated to the ISM. And at this point, when the jet is transitioned from this wind to a stationary medium, something has happened. There is a shift in the jet geometry. The geometry of the jet changed from parabolical into cylindrical. Now, at this case, at this situation, if you remember, I told you that if this flow expands and is not accelerated, the configuration has become dominated by toroidal field. Now, when the jet is becoming conical, causal connection between the different points on the jet is regained, and Hooke stress becoming effective again. So now we are in configuration dominated by toroidal field. Hooke stress is effective, so it contracts the jet. And this contraction creates very narrow nozzles, okay? And in these nozzles, energy can dissipate, okay? The formation of these nozzles is actually something that we can see. For example, the HST1 knot in M87 is an example for a possible location for such a nodule. This knot is very luminous in frequencies between radio in wavelengths between radio and X-ray. It shows massive energy dissipation, and it also, if you look at the plot below, it shows a change in the jet geometry. The distances smaller than HST1. By the way, this distance is about 100 parsec from the center. Sorry, if you untilt it, there is the jet is pointing about 50 something degrees from us, and the actual distance, the distance is thought to be about 100 parsec. So inside this 100 parsec, the jet has a parabolic shape, which is typical for collimation by a wind, and here there is a shift in the geometry of the jet. And we're thinking that maybe this shift is shows that there is actually a nozzle that is formed, and the energy is dissipated in this nozzle. Okay, so now let's focus on the physics of this nozzle, and let's try to see how can Kink instability grow in such nozzles. So first of all, as I told you before, Kink instability requires causality across the jet, so these things can start wobble, and there is enough time to evolve. Nozzles can have both because the nozzle is narrow enough, and the typical velocity of the plasma as it flows through the nozzle is slow. Okay, actually, in 2016, in a work of global simulations of GRMHD simulation, me and Sasha Shekovskoy showed that within the nozzle, about half of the jet energy is actually getting dissipated by internal kink modes. The problem with this global simulation were that we could not study the actual physics of this kink mode. For example, we could not study the conditions for their excitation, and we could not study the relaxation condition. And the relaxation condition is important because if you don't know the relaxation condition, you don't know whether this half of magnetic energy that is getting dissipated is a robust thing or is something that is only typical for the simulation that we run. So this set us on an embarkment to do a follow-up study that I did with several associates. And there what we did is that we ran local simulation. We ran simulation of plasma column threaded by helical field, and we studied the growth of the kink instability in this plasma column. So I'm going to show you a movie that will take you through the evolution of this kink mode and the various situation that is happening there, and I will stop at this point, and I will describe you what is happening there. So we're starting with again with a column of plasma threaded by helical field. What I'm going to show you here is the JZ, which is basically the rotor of the B5 component. Okay, and as the simulation begins, the kink instability starts to grow. You see how the column starts to twist. Okay, kink instability entered the nonlinear phase, and the kink mode that are growing begin to merge with each other. This growth, this sets, I just want to pause here for a second. This sets a helical current sheet. You can see it here in this figure, in this region where these kink modes are merging with each other, and we're getting enhanced reconnection. And there we have a current sheet, and in this current sheet we have energy dissipation. With time, this helical current sheet starts to break into small structure, and this small structure goes into a turbulence configuration, and I start to have a stochastic dissipation in the jet. The configuration continue, the dissipation continue, and the relaxation condition, the dissipation via this kink mode, the kink mode stop growing when we get to a state where the current inside the jet is proportional to the magnetic field at each point. This condition is known as the Tyler state. This state is actually known for quite a long time in the community of the tokamaks, which are also studying magnetic fields, only their idea is to avoid dissipation of magnetic field in order to get cold fusion, but this is a different story. But this condition is actually known in this community, and we actually showed that this is also happening in relativistic jets. Okay? So in principle, what we showed is that indeed about 50% of the toroidal magnetic energy getting dissipated in this process, the dissipation is basically, the reconnection is basically driven reconnection. The different lobes of the kink mode are driving toward each other and compressing toward each other and continue to feed the current sheet with new magnetic fields. And the rate of this dissipation is actually consistent with the sideways motion of this kink mode. Once the dissipation relaxes, turbulence dissipation can continue. The turbulence continue to stay in the jet, and they continue to dissipate energy, however, at a much slower rate. Now, if we move back to an astrophysical system, if the kink dissipation is happening, if the kink instability is happening in the nozzle, the turbulence can continue to dissipate energy also above the nozzle, along the jet. However, the efficiency of this dissipation is still unknown. We are now starting a new study with a more advanced, much better code, much faster code that was developed by Bart Ripperda, which is now a postdoc at the CCA. And this code is basically a dissipative MHD code. Okay, it's not an ideal MHD, which will allow us to track actually the dissipation better, and it's also an MRI code. AMR code, sorry, and this will allow us to track the turbulence at a better resolution and actually follow them to a longer time, and hopefully we'll be able to understand better this phase of turbulence dissipation. So it's definitely not the final word on that. So we know how the dissipation evolved, we know how kink instability evolved, but in order to understand how this thing emits energy, it is not enough to do MHD simulation, because we need to know what is happening to the particles. We need to know how particles are accelerated. And for this type of study, we cannot use MHD code. We need to do a different type of code. These are peak codes. Now, peak are particles in cell. They can actually calculate the individual, the Lorentz forces that are applied on each individual particle or individual groups of particles. But the problem with these peak codes is that they work on typically on a much smaller scale than the MHD. If I can simulate a whole system in MHD simulations, in peak simulations, I'm very limited in the size of the box that I can simulate. Nevertheless, in a project that I did with Sasha Filipov and Jordi Dabenlar, he is now a postdoc at also at the CCA and Columbia. Sorry. So what we did is that we ran large-scale peak simulations with the same configuration as we did with the MHD. And we show that if the peak simulation have enough scale separation between the small Larmor radius of the simulated Larmor radius and the large size of the box, the system evolved, the overall evolution of the system is very similar with the MHD evolution. As you can see here in these images, the top one is the MHD simulation, the bottom one is peak simulation, and you can see that the kink instability actually evolved in a very similar in these two simulations. So using these peak codes, we're actually able to track particle acceleration within the current sheets, as you can see here in this nice GIF. This is shape of the currents within the jets, and you can very nicely see the helical current sheet that evolved inside the jet. And we actually saw that this acceleration is occurring. It's a two-step procedure. First, when these current sheets are evolved, particles are accelerated there, but they develop power law tails, but these tails are very steep. They're not shallow. They are very steep with typical alpha index between -5 to -3. The reason is because for those of you who a little bit know about peak simulation, we have within this current sheet we have also magnetic fields that are along the electric field. Is known as a guide field, and the acceleration in these types of current sheets is not very efficient. Secondly, once the turbulence acceleration kicks in, the turbulence is also adding energy to the system, but this energy comes mostly as heat and not as a power law. So particles are getting power laws when they are accelerated inside current sheet, and then they are heated up. Here I show an example for two particles that are undergoing actually two separate accelerations. Particle number one is mostly accelerated on the periphery of the jet, and it is accelerated within this current sheet. The acceleration is not very effective. The Lorentz factor is increased by a factor of a few. Okay. The second particle is accelerated at the center of the jet, at the core of the jet. Their turbulence acceleration is most effective, and you can see that this acceleration actually can increase the Lorentz factor quite a lot. But these types of particles will not grow a very hard tail. Now, this simulation, though they could follow very well the particle acceleration, they are still limited, because the limitation with this simulation is, as I told you, is the scale separation between the size of the box and the number of cells that we can resolve the current sheet in. And we could not fully resolve, for example, the growth of plasmoid within this current sheet. And plasmoid acceleration with this plasmoid gives a second order Fermi mechanism, which actually take your tail and make it somewhat harder and extend it to much higher energy. So we are now planning a follow-up study that will study the actual conditions within this current sheet, and we hope to better understand this particle acceleration mechanism. So again, this is definitely not the final word on this subject. So another nice implication that comes from this kink instability within nozzles is that we can try to refer it to some types of flares that we see in blazars. These flares are very unique, because what they show is that there is, during the flare, which you see here in the R band, there is an increase in the polarity of the radiation, and also the polarization vector rotates over a few hundred degrees. Okay, this is a very indicative signature. And we are now trying to work, me and together with a student of mine, Gali Birnbaum, we are now trying to work on developing a tool that can calculate, that can analyze the time-dependent polarization from a relativistically magnetized plasma, and try to see whether the passage of a plasma blob through this nozzle can give you this type of polarization. The idea behind that is, as this plasma passes through this blob, it actually starts to rotate, and the magnetic field becoming stronger as it compressed before it gets dissipated. So the emission is becoming dominated by this blob is becoming actually start to emit, and we hope that there is a chance that what we see is actually this rotation of the polarization vector due to the actual rotation of this blob. But this is a work in progress, and so stay tuned whether we'll be able to do it or not. So here I will conclude the first mechanism. So basically what I showed you so far is this kink instability and how it can dissipate a relatively large fraction of the magnetic field from the magnetic energy from the jet. It actually can relieve the jet from about half of this magnetic energy. So it's a very nice way, a very effective way to take highly magnetized jets and to turn them into something else. The problem is that there's something else, because the kink instability basically stops when the thermal pressure is roughly equal to the magnetic pressure. Okay, and in this case, the flow that comes out of the nozzle, you can think of it as like a hydromagnetic jet. On one hand, it cannot efficiently shock because sigma is about 1. On the other hand, it cannot fast reconnect, again, because sigma is not very high. So the problem with this type of jet is that we cannot generate a very highly effective dissipation processes above this nozzle. Very highly efficient radiation that we see, like in gamma ray burst. It's very hard to form them from this hydromagnetic fluid. Now, dissipation via turbulence above these nozzles may help in relieve more than of the magnetic energy, allowing this the fluid to shock, but we still don't know enough whether if it is effective or not. A second problem within this that this mechanism has is that the dissipation sites are located far from the black hole where the collimation occurs. So they cannot explain incident where we see emission coming from very close proximity to the black hole, and for that we probably need a different mechanism. So this leads me to a second mechanism that I want to discuss, And this mechanism is occur when we have, in order to get, let's say, one step backward, if I want to get a very efficient dissipation in the jet, I need to have some global reconnection that is happening within the jet that relieves a large fraction of the magnetic energy almost instantaneously. The best way to do it is if I will take the direction of the magnetic field and flip them, as you can see here in this image. Now, these two blobs, if they collide, will get a global reconnection between these magnetic fields, and I will relieve a large fraction of the magnetic energy almost instantaneously. Now, in black hole, the jet is launched by accreting plasma with poloidal field and onto the black hole. The rotation of the black hole, due to frame dragging, takes this magnetic field and widen, like I showed you in the simple toy model of the perfect conductor, and this transforms this toroidal field into this poloidal field, into the toroidally dominated jet. So if I want to switch the direction of the magnetic field in the jet, all I need to do is to switch the direction of the poloidal field within this accreted loop. So this idea is actually first was thought by Kyle Perfley back in 2015, and he investigated that, and there was also follow-up studies, and these studies actually used GR force-free simulation. Now, force-free simulation, as their name, as you may imagine from the name, they don't include forces. They only calculate the electromagnetic interaction in the grid. So you cannot simulate, for example, you cannot account for gravitational pull of the black hole. You cannot actually simulate the actual physical motion of this loop. So the loops are basically set as boundary conditions that are propagated by hand toward the black hole to form the jet. So question like, can these loops survive this travel in the disk, or what is the efficiency of the jet? These are questions that cannot be answered in these types of studies. So basically what we did, me and my postdoc Anya Chashkina and Amir Levinson, is that we run GRMHD simulation with these types of configuration, with loops with opposite polarity inside the disk, and this simulation can actually track the physics in the disk, and we try to investigate what is happening to how these jets are launched. Okay, so I'm going to take you quickly through the activation modes of this configuration, starting with a single loop. Assume we have a disk, and we have a single loop that is accreted onto the black hole. Now, when this accretion starts, we can think of two phases that this loop is undergoing. Now, in this movie, I'm going to show you the density. This is the black hole. This is the edge of the disk, and here below, I'm going to show you the mass accretion rate and the magnetic flux that is accumulated on the black hole. Now, as the simulation begins and the accretion starts, initially, this black hole, okay, my computer is a little bit slow, so let's see if we can. Okay, here, the simulation begins, the accretion starts. These black lines are the poloidal field lines. This is a 2D simulation. And what you can see from here is that in this initial phase, I'm going to stop the simulation for a moment. Okay, this is continue. Okay, one moment. Let's start from the beginning. I'm using a replacive computer, and it's not very strong. Okay, so here the simulation begins. So initially, I'm accreting mostly large-scale poloidal field, and you can see this poloidal field here on the image. And what you can see is that there is a phase which is known as MAD, which is magnetically arrested disk phase, where I'm accreting large-scale magnetic field. The m dot, the accretion rate, and the flux basically fluctuate between high mode and low mode, but they are correlated with each other. I'm going to discuss this soon. And this gives an intermediate jet launching. The jet is actually very powerful jets are launched. Then the system is transforming into a second phase, which is known as sane, which is called, it is the initial of a stable and normal evolution. In this phase, the system is accreting mostly small scale fields, and the accretion does not correlate with the flux on the black hole anymore. I'm accreting large masses, but I'm not accumulating flux on the black hole. And basically, in this situation, I have no lead jet launching, a very weak jet launching. So mad state, I have an intermediate powerful jet launching. Same state, I have no jet launching. Let's look a little bit closer about this, what is happening within this mad state. So again, I have a flux that is accumulated on the black hole that is coming with the accreted material. Now in this phase, the pressure, the tension, the magnetic tension, or the pressure, the magnetic pressure are basically dominated the accretion. So magnetic pressure is larger than the ram pressure of the fluid, and the magnetic fields which have opposite sign in this above and below the equatorial plane, the magnetic field is starting to push away the accreted material and start to reconnect on the horizon. Sorry, on the equatorial plane. As it reconnects, it grows some plasmoid, but most importantly, this whole configuration of magnetic field changes. You see, these magnetic fields are no longer connected to the black hole. Since I have very high conductivity, this is basically serve as a blockade. It blocks the accretion. So the accretion is magnetically arrested. That's why it's known as magnetic arrest. But this reconnection also reduced the magnetic pressure. Ram pressure is built up on this side of the barrier, and eventually this fluid is able to push back, and we go back to state A, and this is the reason for this fluctuating behavior. Okay. So this is in a single loop state. What is happening? What will happen when I have several loops? So if I will turn on this movie, the first loop, as it accretes, it goes mad just like the single loop state. Okay, you can see here this mad state, but then something is happening. The something that is happening is that you can see it here on the right corner. The second loop start to comes in. As it comes in, it will start to compress the first loop. Okay, with these lines have opposite polarity. This is one direction of polarity. The dashed line are the opposite polarity, and the second loop will start to compress the first loop. And what it will cause the field line of the first loop to reconnect upon themselves, and the first loop will basically disappear. It will reconnect away. The reconnection will occur here on this plane, and here, and basically these field lines have opposite direction. And if I will continue the movie, you can see this loop reconnected away. Flux is now accumulated with the opposite polarity on the black hole, and a second jet is launched. So basically, I'm able to launch this striped jet, a jet with one polarity, and then I switch loops, and the second polarity jet is launched. Okay. Now this is 2D. What is happening in the 3D? So in the 3D, the situation is somewhat similar. What you see here is a top view on this side of the accretion. On this side of the accretion, of the figure, sorry, there is a side view. And what you see here is that the system is actually going into a similar mad phase where reconnection starts. However, the reconnection is not uniform in this case, because this is a 3D, this is a whole plane, this is not just a line. And since the reconnection is not uniform, matter is able to accrete along region where the reconnection rate is relatively low. So I'm never able to completely stop the accretion, but the accretion rate decrease. What it gives is that it gives a jet launching which is more smooth, not without these edges. Okay? If I will continue the simulation, okay, wait, here, if I will continue the simulation, here the second loop will come in, and again, I will have a switch of the polarity, and an opposite polarity jet will be launched. So the global features are similar to the 2D case, although the behavior is much smoother. Okay, in this situation where the loops are switching, some interesting stuff are happening. Here I'm taking a freeze-in on a situation where the first loop that you saw here with solid line is starting to be replaced by the second loop, which you see here in dashed line, and this is the current sheet that is formed. These field lines have opposite direction, poloidal direction, and they start to reconnect. And as they reconnect, I'm creating a current sheet here. And when a current sheet is formed, I also create plasmoids. So during the reconnection episode, I have very powerful current sheets and very energetic plasmoids that are formed. These plasmoids are formed first on the equatorial plane, during the mad states and also during this loop switching episode, and more importantly, along the jet boundary. And these plasmoids are formed, they start to be pushed away, they accelerate, and they start to become larger and larger. And at later time, they may evolve into some radio blobs that some of you are aware of that we see in blazars. I'm going to show you a movie of how this thing evolves. Okay, here you can see this loop switching episode, and you see the growth of the plasmoid that are grown on the side of the jet and along the equatorial plane. Okay, the movie is not smooth because unfortunately my computer is not strong enough. Okay, this is the entropy and this plasmoid. If I will run this movie again, you will see that these plasmoids are becoming quite hot. Also the current sheets, and actually within these current sheets, I can have particle acceleration, and the emission, the expected emission, should be at least in the X-ray regime. Okay, so the nice thing about these current sheets that they will likely emit X-ray radiation. This X-ray radiation can actually illuminate the disk. Now, some of you some of you that are doing the observation of the disk know that there is a problem with radiation that are coming from the inner part of the disk, which there is an excess of an X-ray emission that is coming from it, and this led some investigators to think that there is to these models that are known as the lamppost model, where they infer some unknown object that is located above and below along the axis of the black hole, and it is illuminating the disk with X-ray radiation. These blobs that we see here and these current sheets may be such a source. Since I'm running out of time, I wanted to talk a little bit about the black hole shadow, but maybe we will keep it to the questions, because I think I want to leave a little bit time about the question. I would just say that if you will ask me, I will talk a little bit more about it. I just want to give you the pros and cons of this mechanism. So by taking this opposite polarity loop, I'm able to launch striped jets very efficiently and get effective dissipation at large distances, because these blobs with opposite direction of magnetic field, as they accelerate, eventually they can collide with each other at large distances. And as they collide, I can get this global dissipation and this very effective and fast emission that maybe can explain some GRBs and some flares in AGNs. Second thing that I showed you is that the second thing that is coming from is that small-scale dissipation produce some observables in AGNs, like maybe like the radio blobs or the lamppost models. There are, however, some drawbacks to this mechanism. For one is that the loop size needs to be not too small. If the loop size is becoming smaller than about 10 RG, I don't have time for the mad states to evolve, so the launching efficiency drops considerably, and I'm unable to launch very efficient jets. Another problem is that I cannot form the loop too far from the black hole, because as they loop get closer and closer inwards, they start to be affected by turbulence inside the disk, and basically this turbulence mode are destroying the loops. So I need to continuously produce them within something like 100 gravitational radii from the black hole in order for this mechanism to be effective. And the main question that is coming from it, can this be done? Can I form these loops continuously with loops with opposite polarity continuously within this radii? There are some initial studies that are being made by Sasa Tchaikovskoy and his group in a new code that they are now working on, which is called Hammer. The results at the moment are inconclusive, so we don't know if this is possible or not. So I will conclude here. What I showed you is that several activation and dissipation channels in point-in flux dominated jets. I first discussed the Kink instability channel, which work in collimated jets. It operates at intermediate distances. it dissipates about half of the magnetic energy, possibly more at longer distances through this turbulence dissipation, and it could very well be responsible to massive HST1-like knots and maybe some laser flares. Then I showed you how to produce striped jets from opposite polarity loops. I showed you that this can lead to quite naturally lead to intermittent jet activity, which we see in many objects, for example, in GRBs. It gives an easy way to get a global reconnection at large distances from the jet. Current sheets and plasmoids close to the black hole can supply photons for lamppost type models, and also produce subparsec radio blobs. And the last thing that I did not talk about, and if you want, I can, if we have time, I can talk about it now, is a little bit how to connect this with the black-hole shadow emission, but this is a little bit lengthy, so that's why I chose to skip it. So I will stop here. Thank you very much.
So thank you, Omer, very much for this very nice talk. For me, if you can say something about the black hole shadow, it's okay, because it was very interesting, the talk for me. But let's see if there's any question, and then you can.
Okay, let's see if there are questions.
Yes. Yeah, because we have time yet. Yes. So.
Okay.
If there, just let me know. You can, if anybody has questions, they can unmute their phone now, their microphone.
I have a question.
Yes.
Okay.
Yeah, hi. Thanks for the very nice talk. So in the first set of simulations that you showed, I'm curious on how you make these nozzles in the simulation, because you need a disk wind and you need a stationary medium, right? So how do you get?
So basically, in order to create a nozzle, it is enough to launch the jet into a stationary medium. Let me, maybe I can share the screen again. You see the presentation now? I'm completely lost. I have no idea how do I reshare the screen? Let's see. One moment. Give me a second. Okay. Okay. Yes. But I will restart the presentation. Can you see it?
Yes.
Okay, good. So, okay. So basically, in this type of simulation, what we did is that we launched the jet in the same way that I showed you initially, of taking a conducting sphere attached with radial field lines and rotate it, and this will launch a jet, and the jet will, and we push the jet into stationary medium. Now, what happened as the jet evolves, it grows a region inside close to the jet where the magnetic pressure stresses along the field lines dominate everything. And in this region, I have a conical evolution. So this is similar to what is happening in wind environment. And at some point, it starts to feel the pressure from the environment, and then the collimation is occurring.
Okay.
But the drawback of that is that I need a very large dynamical range. Mm-hmm. And if I'm using a global simulation, it means that I'm very limited in the resolution of how I can study the nozzle.
I see. Okay, thanks. Very, very impressive.
Okay.
So we have a question in the chat. I will read it. Eduardo, if you want, you can unmute. But he,
yeah.
Okay, Edu, yes, go ahead.
No, first, when you show the in M87 the change of the
this one.
Yeah, exactly. The jet is parabolic at lower distances and then becomes conical.
Yes, it becomes conical. It is not becoming cylindrical, as one would expect, but we don't really know what is happening there. It could be that what you see here is somehow this emergent, like it's getting very narrow and then it goes out very slowly. And it could be that it is going into a very low density environment, and in low density environments, actually we expect it to expand relatively conical. Okay, but the main the main thing is that what is happening here, what is happening in this situation, and it could be that this is a nozzle, and it could be that this is not, but something is happening there, and we still don't know.
Okay, thank
Does
you.
this answer the question?
Yes.
Okay.
Okay, Maria, yes.
Yes, I have a couple of questions. Thank you, Omer, for this talk. It was really clear talk.
Thank you.
I don't work on jets, but I am very interested in particle acceleration. And I have a question about the Kink unstable case. You mentioned that you found particle acceleration, and I am interested in the most efficient one. But you mentioned that turbulence is involved in this one. And I am guessing can you tell if this is a first order or second order process?
Oh, that's a very good question. We think that this is a second order process, but this is something that we need to further investigate. One of the things that we want to do within this dissipative MHD code is that we think that we'll be able to track turbulence better, and we'll be able most naturally be able to track their motion. And their motion from the peak simulation seems to be random. So if it's a random motion, it's like a second order for me. But we don't. I don't think, since all it did was heating, I don't think we got to the second order for me, because we couldn't simulate it long enough.
Okay. So you're just starting to see some indication of effective acceleration, but it's not really turbulent yet.
It's not really this classical second order turbulence acceleration that Lazarov is seeing, and not yet, at least.
Okay. And then I have a second question that is also related to that. You mentioned that after the nozzle, you would expect also turbulence. And that this turbulence will be actually feeding by the kink, right?
So this is so in the simulation that we run here in this study, or if you want here in this study, okay. So this is a stationary column, okay. It's not moving. Maybe it's. I will show it here. This is a stationary column. It's not moving. Okay. So what we see is that it starts to kink, and then the kink relax, and then I have turbulence, and the turbulence slowly evolves, slowly relax, and I have very slow dissipation. Now, in real life, all this thing is moving. So this kink, we assume that is happening at the nozzle, and as it relaxes, it exits the nozzle, and then the turbulence continue. Now the turbulence will continue. This flow continue to expand upwards, and this is happening at the rest of the jet above the nozzle. So the question is how effective this dissipation, and how low can we get sigma above the nozzle? And for that, I still don't have a definite answer.
Okay, so but you are not expecting to have actually this. You mentioned that the structure is moving, but you won't expect the turbulence to be continuously fed. I mean,
whether they are continuously initiated or they're just relaxing from the initial kink. So that's actually also a good question. I would think that they will mostly continuously relax. Whether there is some interaction with the medium can pump more energy into the jets, this can maybe re-excite some of the turbulence, but it's a more of a quantitative question that I don't have answer to.
Okay, because that would be also interesting for the acceleration of particles, because if actually it's happening because of the turbulence itself, and if you have strong turbulence, then you would have a continuous acceleration, let's say.
Exactly, that's true. Here you can see it here. In this region, we think that this is where the kink instability, this is the nozzle where the kink instability kicks in, and above it, this is where the turbulence regime can work, whether these turbulence are only relaxing or continuously fed by some, I don't know, some acoustic modes from the interaction with the medium. It's a good question. I don't know.
Okay, thanks a lot.
Okay, is there any other question? Okay, Omer, if you're okay with comment something on the black hole
Yes,
shadow, we are all waiting.
no,
I think.
no problem. I will
Because
happy.
it was a very nice talk.
To do it. Okay, so let me switch to the slide. Okay, so for those of you who are unfamiliar with this black hole shadow observation, the idea is as follow. Okay, we have basically around the black hole, we have around the rotating or stationary black hole, there is this radius where if you take a photon and the photons will start to circulate, it will do many, it's like it will do infinitely number of turn before it can fly out. Now, if you assume that the whole of the emission region is optically thin, okay, and you have a plasma that is emitting and it continuously emits in this radius, then the emissivity, the number of photons that are accumulated within this radius will increase and increase with time, and eventually you will see a very bright ring coming from this. Now, at lower radii from this, at lower distances from this radius, any trajectory will end up falling into the black hole. So any plasma that is emitting from there will look dimmer. So everything inside this radius is called the black hole shadow. So black hole shadow is actually extended to a few times of the gravitational radius outside of the true horizon. Okay, and so these observations that were done by the EHT, they claim that they saw this ring, this photon bright ring, and the dark spot inside are these black hole shadows. And indeed, the size of this, the diameter of this very blurry ring is about 10 Rg, which is roughly what we expect for the black hole shadow. Now, in part of their enormous effort, they made numerous number of papers, and they also tried to come out with some emission mechanism that can explain this. So what they did is that they ran GRMHD simulation, quite similar to the simulations that we run, and they tried to see whether a mad state or a sane state can explain what is happening inside this ring. The problem is that they don't have any emission models. So what they did is that they made some assumptions. The assumptions that they made is that the emission is basically thermal. Okay. They also assumed that the energy within the electron is about a third of the energy in the ions. Okay. And the typical temperature of the electron is about 10 MeV, something like that. And the beta parameter is about unity. This is roughly the model parameters that they assume to get the emission from this ring. Now, if we look at our results, some of their assumptions are actually come in conflict with the results that we are getting. To remind you, in the mad state, we had low and high accretion modes. Okay, in the low accretion state, when we had the reconnection, I want to show you. Where can I show it to you? Yes, I want to show you here. Okay, in the low accretion mode, when we had reconnection, we had a lot of plasmoids that were formed on the equatorial plane. Now, the typical temperature for this plasmoid, the ion temperature for this plasmoid, were a few GeV. Okay, you see rho over P is about unity. So this means that if I am looking at their model, where the electron temperature is about 1/3 of the ion temperature, I am getting an electron temperature which is much brighter than what they expect. Also, the current sheet themselves, emission from the current sheet is expected to be non-thermal, so the emission from this low accretion state is not expected to be very bright in radio. And this observation is basically radio observation. In the high accretion state, the problem is that I have a jet formation and I have strong magnetic fields. And in order to get this emission, they actually needed the jets to be very weak, because if they will have a very effective jet, they will be blinded by the jet. So one of the conclusions that we're getting in this Orion simulation is that the mad states are inconsistent with the observation of the black hole shadow. Another thing that we saw from the mad state, remember that this mad had high and low accretion mode, we expected to see variability in this image at time scales of the order of these small changes that are happening during the mad state, and the time scales are on the order of about something like larger than something like 100 Rg/c, which is like months in M87 scales. So one prediction that we're getting from our model that this picture is, if we are indeed looking at the mad state, this picture is expected to vary at this time scale. Now, when I try to compare the properties that we're getting in our sane state, sane, remind you, it's a steady accretion and a very inefficient formation of the jet because the typical size of the loop is relatively small. Now, during a sane state, their conditions are roughly okay because the typical temperature that they need for the electron is higher, more like 100 MeV, not like 10 MeV, and this is roughly what we are getting from. So from our simulation, at least, the sane accretion mode is more consistent with the black hole shadow observation than the mad accretion mode. And this is all that I wanted to say.
Okay, well, thank you very much. Is there any other question?
I have a question related to that, the recent report of polarization from the emission detected. Is this, or have you think of the consequences that the reported polarization has on firstly the emission mechanism, right? Can you comment on this?
No, because I have not fluent enough in the literature of the polarization measurements, unfortunately, to say anything smart about this. What I do know is that the one thing that I do know is that they are able to get a reconstruction of a helical field. This is basically all that I know about this thing.
Okay.
Sorry.
No, it's okay. Thank you.
It's a numerous number of papers. Just sitting down and reading them, you need.
Yes, I understand.
Make too much time.
Yes. I have a few of those also. So if there isn't any more questions, we thanks a lot. Again. Oh, sorry.
Sorry. Do we have time for another question, or
Omer is okay? For me, it's okay.
I'm available.
Okay.
Okay, thanks. Yeah, very nice talk. I had a question for the last part of the talk, the current sheet simulations you showed last. You mentioned that those blobs have very high entropy, right? And yeah, and you mentioned that if I remember that those could be detected in X-rays in principle, right? So my question is how does change if you change the thermodynamics? I don't know if you mentioned that what kind of thermodynamics you're assuming here, and how robust is the entropy or temperature? Yeah.
Okay, so a few comments on that. So first of all, the X-ray will come actually from the current sheets, not from the blobs, because within the current sheets we have the particle the acceleration to power law tails. Within the blobs, particles tends to be more thermal. But our simulations are definitely not converged because the resolution is still not good enough in order to track the actual plasmoid change that we see here, because there is another acceleration that is coming from the collision between these blobs. We need much higher resolution simulation for that to understand better what is happening there. And this projects, some of these simulations are actually underway. A group led by Sasha Filipov and Bart Riperda are now running such high resolution simulation on a single loop, and we're planning to collaborate with them to run these high resolution simulations on several of these loops to see if the structure of these current sheets is going to be considerably different.
Thank you.
Okay, so I still don't know how robust the structure seems to be quite robust, because this global picture of a loop reconnecting upon itself, disappearing, clearing the way for the second loop to come, seems to be quite robust. So if the loop is reconnecting upon itself, you expect to have current sheet, you expect to have plasmoids that are formed. Exactly what are the temperature and everything, this actually depends on the code.
Right. Excellent. Thank you.
Okay. So again, we thanks Omer for this very nice talk, and thank you everyone for participating in the seminar of the Institute. Thank you.
By the way, the paper for the last subject, we expect that will be out this week, so you're more than welcome to look at it, and maybe if you have more questions, I will be happy to answer via email.
Perfect. Thank you. And thank you, everyone.
Bye. Thank you.
Bye. So, thank you very much, Omer. It was a very nice and clear talk.
Yes. Oh,
and very
thanks.
interesting.
Thanks. I didn't expect to be able to talk about everything, so I actually was surprised that I made it. So
yeah, it was very clear. And well, so stay safe and hopefully
yes, you too.
Correctly.
Yeah, and hopefully we'll talk again.
Yes, of course. And when we are able to travel again, let's see we can arrange that for the university. Yes. So
yes,
stay safe.
Bye.
Bye.
Bye, everyone. Thank you.
Bye, Maria. It was good to see you again.
The same to you. Many thanks for your talk. It was really clear. Yes. I loved it.
Thank you.
Okay.
Thank you.
Bye-bye. Stay safe.
Bye-bye.
Bye.